Hey there and welcome. Ever wanted to crack a secret code? Well, today, that's exactly what we're going to do. We're going to learn how to draw a blueprint for an atom, taking something totally invisible and making it something we can actually build and understand. Let's get into it. So, that really is the big question, isn't it? How in the world do you draw something you can't see? I mean, atoms are impossibly small. The answer? You don't. Instead, you create a simplified map, a kind of blueprint. And that's where models come in. Think about a blueprint for a giant skyscraper. It's not the actual building, right? But it shows you everything you need to know. Well, in science, we do the exact same thing. To wrap our heads around ideas that are way too complex, or, in our case, way, way too small to see. And check this out. The reality of an atom is actually kind of chaotic. It's called the electron cloud model, where electrons are just zipping around near the speed of light. It's frankly mind-bending stuff. But for us, we're going to use our trusty blueprint, the Bohr-Rutherford model. It's simple, it's clear, and it gives us a perfect snapshot of all the key players we need. Okay, this brings us to Section 1, cracking the elements code. Think of this as our first mission. We need to gather some essential clues. And our master codebook for this whole operation, you guessed it, the periodic table. So clue number 1, and this is the most important one, is the atomic number. This little number is basically an element's unique fingerprint. It tells you exactly how many protons it has, which, and this is the cool part, also tells you how many electrons you're working with. It's the key that unlocks absolutely everything else. And here are the formulas, our secret decoder ring, if you will. It's so simple. The number of protons, that's just the atomic number. The number of electrons? Well, in a neutral atom, it's the same as the protons. And the neutrons? Just a little subtraction. Take the atomic mass, subtract the atomic number, and you've got it. That's it. All right, let's move on to Section 2. Now that we know how many electrons we have, the next big question is, where do they all go? Turns out there are just two simple rules we need to follow, the rules of the rings. Rule number 1 is a fantastic shortcut. Seriously, just look at what row your element is in on the periodic table. That row is called a period. And whatever that number is, that's exactly how many rings or shells you need to draw. If it's in period 3, you draw 3 rings. Boom, done. And rule number 2 is our other big cheat code. Look at the elements column, which we call a group. That tells you the number of valence electrons. Now, these are the really important ones. They're on the outermost ring, and they're the ones that get involved in all the chemical action. And this is your go-to guide. For groups 1 and 2, it's a piece of cake. The group number is the number of valence electrons. For groups 13 through 18, here's the trick. Just look at the last digit. Group 13 has 3, group 17 has 7. See the pattern? And for now, we're just going to ignore those transition metals in the middle. Okay, last rule of the game. Each shell has a maximum capacity. The first shell, the one closest to the center, is pretty exclusive. It can only hold 2 electrons. After that, the next few can hold up to 8. The golden rule here is you always have to fill the shells from the inside out. Fill up one before you move to the next. All right, code breakers, this is it. Section 3, putting it all together. We've got our clues, we know the rules, so let's put it into practice and draw a real element. Let's do fluorine. Let's do this. Step 1, find the particles. We look at our codebook, the periodic table. Fluorine's atomic number is 9. Bam. That means it has 9 protons. Its mass is 19. So 19 minus 9 gives us 10 neutrons. We just write 9p plus and 10n in the center, draw a circle around it, and there you have it. Our nucleus is done. Step 2, the shells. Remember the shortcut? We just find fluorine's period. It's in period 2. So what does that mean? Yep, we draw exactly 2 rings around that nucleus we just made. Simple as that. Step 3, let's place those important valence electrons. Fluorine is in group 17. Remember the trick? We just look at the last digit. So it has 7 valence electrons. Now here's a pro tip to keep things neat. Use the clock method. Put 1 electron at 12 o'clock, 1 at 3, 1 at 6, and 1 at 9 times before you start pairing them up. It's so much cleaner that way. We are on the home stretch. Okay, let's do the math. We know fluorine has 9 electrons total, right? We just placed 7 on the outer shell, so 9 minus 7 leaves us with 2. And where do they go? In the only spot left, that first inner shell. Now, the final check.
Let's count them up. 2 on the inside, 7 on the outside equals 9 electrons. And we have 9 protons. It's a perfect match. We did it.
And that brings us to our final section. Now it's your turn, because what you've just done is more than just follow steps. You've officially cracked the atomic code. Just think about this for a second. With a few simple rules we just covered, you now have the key to draw a blueprint for any of the first 20 elements on the periodic table, from hydrogen all the way to calcium. That is a huge chunk of the chemical world you can now build from scratch. I want to leave you with this quote from a guy named Howard Skipper. He said, "A model is a lie that helps you see the truth." And that's perfect, right? Our drawing isn't what an atom actually looks like, but it's an incredibly powerful tool that helps us see the fundamental truth of how it's built. So that leaves us with one last big question. Now that you can build the blueprint for a single atom, what do you think comes next? It's all about understanding how they connect. Because knowing the structure of one atom is the first step to figuring out how they bond together to form molecules and compounds and, well, everything around us. So keep cracking those codes.